Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's class, we will discuss some more things on linear transformations. This is my second class on linear transformations. In this class, let us quickly recap the definition of linear transformation and kernel and range of linear transformation. In today's class, let us prove operation of the differentiation is a linear transformation, and we will discuss some of the applications of kernel in physics. Finally, we solve problems on linear transformations to explore more things from linear transformation. Let us first quickly go through the definition of linear transformation, which we have discussed in detail in the previous class. So, linear transformation T from a vector space V into a vector space W is a rule that assigns to each vector x in V a unique vector P of x in W such that P of U plus V is equal to P of U plus T of V for all U V belongs to V, and T of Cu is equal to C times T of U for all U belongs to V and scalar C. So, a linear transformation is a function from one vector space to another vector space with two properties. These two are the properties. T of U plus V is equal to V of U plus V of V, and T of C times U is equal to C times T of U for all U belongs to V. If these two properties are held by a function from one vector space to another vector space, then we call that function T as a linear transformation. This is the definition we have seen in the previous class and discussed in detail. And this is another definition which we have gone through. The kernel of a linear transformation. Kernel or null space of a linear transformation T from V to W is the set of all U in V such that P of U is equal to 0 bar, the 0 vector of W. So, kernel is the set of elements of V which are mapped onto the 0 vector of second vector space W. It is denoted by kernel T, that is the symbol for that. This is the set notation for kernel T. Kernel T is equal to set of U belongs to V such that T of U is equal to O bar. I am calling it as O bar, the 0 vector of W, which Venn diagram will be like this. This is U, this is V, and this is W. These two are vector spaces. T is the relation, is the function between these two vector spaces, and this is the set kernel P whose elements are mapped to the 0 vector of vector space W. So this is the kernel, and the range of a linear transformation T from V to W. The range of a linear transformation T from V to W is the set of all vectors in W of the form P of x for some x in V. For some x in V. So range of a linear transformation is a subset of W. It is denoted by R of T, that is range of T. That is range of P is equal to set of Px such that x belongs to V. Its Venn diagram will be like this. This is a vector space V and this is another vector space W. P is the function from V to W, and this is the set range of T in which each and every element is an image of some vector in V. So this is the range of V. It is clearly a subset of vector space W. In the previous class, we have seen that range of a linear transformation T from V to W is a subspace of W, and kernel of a linear transformation T from V to W is a subspace of V. In today's class, let us do that. Operation, the well-known operation, differentiation, is a linear transformation. Let V be the vector space of all real valued functions f defined on a closed interval AB with the property that they are differentiable and their derivatives are continuous functions on closed interval AB. So let us take a set V whose elements are real valued functions defined on some interval, some closed interval AB. Moreover, they are differentiable and their derivatives are continuous functions on this interval. So that is the set we have taken. That set will become a vector space with function operations, usual function operations. Let W be another vector space of all continuous functions on closed interval AB, which is defined by C of closed interval AB. Continuous functions on closed interval AB. So V is set of all real valued functions defined on AB and differentiable, of course, and W is all continuous functions on closed interval AB. Then our differentiation operation denoted by D here. Let D is a mapping from V to W be a transformation that changes f in V into its derivative f dash. So it is the operation of differentiation defined from V, real valued functions, to continuous function set. Our operation will derivate the function. That is our operation. So in calculus, with two simple differentiation rules, we have derivative of f plus g, two functions. Derivative of f plus g is equal to derivative of f plus derivative of g, and derivative of cf is equal to c times derivative of f. We know pretty well about these two rules. Derivative of sin x plus cos x is equal to derivative of sin x plus derivative of cos x. We are using that formula very frequently. Derivative of u plus v is equal to derivative of u plus derivative of v. Similarly, here f and g are my functions. So derivative of f plus g is equal to derivative of f plus derivative of g. And we know that derivative of some 5 cos x is equal to 5 times derivative of cos x. So we can take out the constant. So here f is the common function. Derivative of cf is equal to c times derivative of f. These two rules are very familiar in derivations. So here these two are nothing but the two properties of linear transformation. T of u plus v is equal to t of u plus t of v, and t of cu is equal to c times t of u. So instead of t, here we have the differentiation operation d. So the operation of differentiation satisfies both the conditions of linear transformation. So the differential operation is a linear transformation. So the kernel of D is the set of constant functions on closed interval A. So kernel is nothing but all the elements of V which are mapped to the zero vector of W. So zero vector is zero function there. So for all constant functions, the derivative is zero. That's why the set of all constant functions constitute the set of kernel of D here. Similarly, the range of D is the set W of all continuous functions on closed interval AB. So if we have taken all real valued functions, the output of derivative functions will be all continuous functions on closed interval AB. So the entire set W will be the range of D. So let us explore some more applications of kernels in physics. The differential equation y double dash plus omega square y is equal to 0, where omega is constant, is used to describe a variety of physical systems. So this equation is very popular in physics. This is used in many places of physics. So these are the areas where this equation is used. The vibration of a weighted spring, the movement of a pendulum, and the voltage in an inductance, capacitance, electrical circuit. In all these problems, you will come across this differential equation. So the set of solutions of this differential equation y double dash plus omega square y is equal to 0 is precisely the kernel of the linear transformation that maps a function y is equal to f of t into the function f double dash t plus omega square f of t. So if you find the kernel of this linear transformation, you find the solution for this equation. So solving this problem is equivalent to finding the kernel of the linear transformation, which maps the function from y is equal to f of t to f double dash t omega square f of t. So let us do some more problems. This is another problem. Let M 2 by 2 be the vector space of all 2 by 2 matrices, and define T is a mapping from M2 by 2 to M2 by 2 by P of A is equal to A plus A transpose, where A is equal to matrix A, B, C, D. Show that T is a linear transformation. So here our M is the vector space of all 2 by 2 matrices. So T is defined from M to M, and P of A is defined as A plus A transpose. To show that T is a linear transformation, we need to prove the two properties. T of A plus B is equal to T of A plus T of B, and T of CA is equal to C times T of A. First, let us simplify the T of A. Let us explore a formula for T of A first using this one. So it is given that A is equal to a matrix, a 2 by 2 matrix of A, B, C, D. So A transpose is A, C, B, D, that is A transpose. So its rows are converted as columns and its columns are converted as rows. Now P of A, our definition, as per our definition, it is A plus A transpose, that is equal to matrix A B C D plus A C B D, that is equal to 2A B plus C, C plus B. C plus B is nothing but B plus C, since these are all scalars. Commutative property holds in scalars, and this is D plus D is 2D. So our T of A is this one, 2A B plus C, B plus C, 2D. This is a 2 by 2 matrix again. So first let us do that. T of A1 plus A2 is equal to T of A1 plus T of A2. Let A1 is equal to A1 B1 C1 B1 and A2 is equal to A2 B2 C2 D2 belongs to M2 by 2. So I have taken two vectors, here two matrices in M2 by 2 matrices set. This is a vector space, of course. Then A1 plus A2 is equal to, adding these two matrices, that is equal to A1 plus A2, B1 plus B2, C1 plus C2, B1 plus B2. This is A1 plus A2. So P of A1 plus A2, that is as per our formula, it is 2A there. So here my A is A1 plus A2. So 2 times A1 plus A2. Here it is B plus C. This is B and this is C. So B1 plus B2 plus C1 plus C2. This is also B plus C. So same as it is here. And this is 2D. D is D1 plus D2 here. So it is 2 times D1 plus D2. This is here A1 plus A2. This can be separated as 2A1 B1 plus C1 B1 plus C1 2D1 plus 2A1 B2 plus C2 B2 plus C2 2D2. It is separated as two matrices. Now this is P of A1 and this is P of A2. So this is the first property of linear transformation. P of A1 plus A2 is equal to P of A1 plus P of A2. This is the first property of linear transformation. Next, let us do that. T of SA is equal to S times T of A. Here I have taken S in place of C, since C is one of the component of the matrix. To avoid confusion, repetition, here we have C. So I have taken another scalar S. For scalar S, SA is equal to, so I am multiplying with S, the matrix A, then I will get SA, SB, SC, SB. And SA transpose is equal to SA, SC, SB, SD. The rows are converted as columns here. That is transpose. So T of SA, that is equal to SA plus SA transpose, that is equal to SA, SB, SC, SD plus this one. I am adding these two matrices. Then I will get 2SA, SB plus SC, SC plus SB is nothing but SB plus SC, 2SD. So this is the addition of these two matrices. So again, S can be taken out of this matrix. That is equal to S times 2A, B plus C, B plus C, 2D. This is P of K. So this is equal to S times T of. So T of SA is equal to S times T of A. That is what we need to prove as second property. So since we proved both the properties, we can conclude that T is a linear transformation. First we prove that P of A1 plus A2 is equal to P of A1 plus P of A2. Now P of SA is equal to S times T of A. So it is a T is a linear transformation. Let us move on to one more point of this one. The matrix is same, M2 by 2 matrix, which is a vector space. We set up all 2 by 2 matrices is M2 by 2. That is a vector space. And T of A is given A plus A transpose. Now we have to find an A in M2 by 2 such that T of A is equal to B, where B should have this property. B transpose is equal to B. B is an element in M2 by 2 such that B transpose is equal to B. Then we need to find a matrix A such that T of A is equal to B. So B transpose is equal to B implies B is of the form A, B, B, B. Since any typical element in M2 by 2 is of the form ABCD, its transpose is ACBD. If both are to be equal, then B must be equal to C. So any matrix which has the property B transpose is equal to B should be in this form A, B, B, B. So let us take one B of this form A, B, B, D. Then B transpose is equal to again A, B, B, D, that is equal to B. So this has the property B transpose is equal to B. If A is taken as A by 2, B by 2, B by 2 and D by 2, then A transpose is again the same matrix A by 2, B by 2, B by 2 and D by 2, and T of A is equal to A plus A transpose, that is equal to this is A by 2, B by 2, B by 2, B by 2, and A transpose is also same A by 2, B by 2, B by 2, B by 2. After adding these two, we will get A, B, B, B. This is the required B. So I find the matrix A by 2, B by 2, B by 2, B by 2 such that T of A is equal to B. So this A is the required matrix in M2 by 2 such that T of A is equal to B. This is one more problem in this one. Again, M is a 2 by 2 matrix. M is the vector space consisting of all 2 by 2 matrices. And T is a linear transformation from that vector space to same vector space. And T of A is A plus A transpose. Show that the range of T is the set of B in M2 by 2 with the property that B transpose is equal to B. So now we have to find a range of T. Let us take one vector, that is a matrix in range of T. Let C be a matrix in the range of T. So C be a matrix. If C is in range of T, then there exists a matrix A in the first vector space M2 by 2 such that P of A is equal to C. Since C is in the range of T. So the definition of range of T, there must be some vector in the first vector space such that P of A is equal to C here. If A is equal to ABCD, then A transpose is ACBD, and P of A is equal to A plus A transpose. That is, we are adding these two matrices, and that is 2A, B plus C, B plus C, 2B. This is P of A. Then C is equal to 2A, B plus C, B plus C, 2B. So any matrix in range of T will be in this form. Then C transpose will be 2A, B plus C, B plus C, 2B. So if you observe that both are same, C is equal to C transpose. So therefore C is equal to C transpose. Therefore every element in R of T is of the form B transpose is equal to B. So any vector in range of T will have this property. B transpose is equal to B. So this problem is also proved, solved. Finally, describe the kernel of T. So for this problem, for this given linear transformation, we need to describe the kernel. T of A is equal to, already seen in the previous one. Then A is equal to ABCD. T of A is equal to A plus A transpose. That is finally 2A, B plus C, B plus C, and 2D. Let us equal this to its zero vector. Zero vector in M2 by 2 vector space is 0, 0, 0, 0. So if P of A is equal to 0 vector, then A must be 2A is equal to 0, that implies A is equal to 2D is equal to 0, that implies D is equal to 0. And B plus C is equal to 0 implies B is equal to minus. So these are the conditions for a matrix A so that P of A will be equal to O null matrix. So if A is equal to, if I replace these values, 0, B, minus B, since C is equal to minus B, I am taking here instead of A, B, C, D, A is 0, B is B, C is minus B, and D is 0. If I take this one, and then A transpose will be 0, minus B, B, and 0, and P of A is equal to A plus A transpose is equal to 0B minus B 0 plus 0 minus B, B 0, which is finally equals to null matrix 0, 0, 0, 0, that is O, null matrix. So matrices of the form 0, B, minus B, 0 are in kernel of T. For example, 0, 2, minus 2, 0. That will be in kernel of T. For any scalar B, 0B minus B 0. This is the form, required form. So I can define kernel T as set of all matrices of the form 0, B minus B 0 such that B is a scalar. So this is about kernel of T. This is one more interesting problem. Define T from P2 to R2 by P of P is equal to matrix of, it is a 2 by 1 matrix, P of 0 and P of 1. In the first row we have P of 0 and second row P of 1. Show that P is a linear transformation. First we do this with the mathematical notations. Later we move on to see the numerical examples also. We know that this P2 is the set of all polynomials of degree at most 2, and we have seen that this is a vector space. So any typical vector in P2 will be in the form P of T is equal to A0 plus A1T plus A2T square. This is a quadratic equation. It may be a linear equation also if A2 is 0. So any typical vector in P2 will be in this form. P of T is equal to A0 plus A1T plus A2T square, where A0, A1, A2 are scalars. Of course, usually real numbers. We are taking real numbers as our scalars. So P2 is a vector space with respect to usual polynomial addition and scalar multiplication, which we have seen in our earlier classes. We know that R2 is also a vector space. Every Rn is a vector space for n greater than or equal to 1. So R2 is again a vector space. Now T is a function from one vector space to another vector space with this property P of P is equal to P of 0 and P of 1 as entries of our 2 by 1 matrix. Now to show that T is a linear transformation, we need to do the two properties, that is P of U plus V is equal to P of U plus T of V, and T of Cu is equal to C times T of V. We need to do both those properties. So it is the definition of P given T. Let us take two elements in P2. Since P2 is the set of all polynomials, I have taken two polynomials, one P of P, another one is Q of P. So these two are my polynomials. Then T of P plus Q is equal to P plus Q is a new polynomial. After adding these two, we will get another polynomial of degree at most 2. So the value of P of P plus Q is equal to P plus Q of 0 and P plus Q of 1. This is equal to P of 0 plus Q of 0. So this function, these two are functions, polynomial functions, can be separated. So P of 0 plus Q of 0, and this is P of 1 plus Q of 1. And this can be written as an addition of two matrices, P of 0, P of 1 plus Q of 0, Q of 1. Now this is T of P and this is T of Q. So T of P plus Q is equal to T of P plus T of Q. Now this is the second property. T of Cp is equal to Cp is another polynomial of degree at most 2. So this is Cp of 0 and this is Cp of 1. This can be written as C times P of 0 and C times P of 1. Now C can be taken out of this matrix. So C times P of 0 and P of 1. This is nothing but T of P. So this is C times T of P. So we have proved both the conditions of the linear transformation. So P is a linear transformation from P2 to R2. This is the second one. For the same T, find a polynomial P in P2 that spans the kernel of T and describe the range of T. So we need to find polynomial P that spans kernel of T. So to find the kernel, first we need to find the zero vector. So zero vector in R2 is O, that is 0, 0. That is zero vector in R2. So if P of T is in the kernel of T, then this must be equal to this 0, 0. So P of 0 is equal to 0 and P of 1 is 0. So P, for a polynomial equation, P of 0 is 0 and P of 1 is 0. That implies both 0 and 1 are the roots of that polynomial equation. 0 and 1 are the roots of the polynomial P of T. So P of T must contain T times T minus 1. If 0 is a root, T is a factor. If 1 is a root, T minus 1 is a factor. So since both are these, 0 and 1 are the roots of the polynomial, T and T minus 1 both are the factors of the polynomial. So the polynomial P of T must contain T times T minus 1 since both are the roots. Hence P of T must be in the form of C times T times T minus 1 where C is a scalar. So this polynomial T times T minus 1 spans kernel of T. So any multiple of this one will be in the set of T, in the set of kernel of T. Null space, that will be the null space. So further, P of T is equal to A0 plus A1T plus A2T square. That implies P of 0 is equal to A1 and P of 1 is equal to, if we substitute 0 here, we will get only A0, these two will vanish. And if you substitute 1 here, this is A1 and this is A2. So P of 1 is equal to A0 plus A1 plus A2. Let CD belongs to R square. Let us take a typical element in R2. Then P of 0 and P of 1 is equal to, this is P of 0 is A0 and P of 1 is A0 plus A1 plus A2, that is equal to CD. If I want to produce a typical element in R2 using this, I must have A0 is equal to C and D is equal to A0 plus A1 plus A2, but I can replace A0 with the C. So C plus A1 plus A2. So for any CD belongs to R, we can find A0, A1, A2 belongs to R such that C is equal to A0 and D is equal to C plus A1 plus A2. So if you take any two real numbers here, for those real numbers, I can find these A0, A1, A2 such that these two relations are satisfied. So I can produce any R2 element using the real numbers. So the entire set of R2 is the range of T. So this is the solution. So let us have a look on the numerical examples of this problem. So I have taken it from the Excel. So let it is 2t square. T square is written in this like this. This is the polynomial. First polynomial p of t is 2t square plus 5t plus 3. This is the constant term. I have taken another polynomial p of t 0t square. For example, I have taken 0t square minus 2t plus 6. So then my t of p after linear transformation, my p of 0 is for this polynomial it is 3. Since you are substituting 0 in place of t, so 2 into 0, 5 into 0 plus 3, that is 3. If t is replaced with 1, 2 into 1 square is 2, 5 into 1 square is 1, 5 plus 3. So 2 plus 5 plus 3, 10. So this is my P of t. After linear transformation, this is my matrix T of t. Similarly, here it is T of q. This is T of p and this is T of q. So if we add these two, I will get another polynomial like this. This is p plus q. So if you add both these polynomials, 2 plus 0 is 2, 5 plus minus 2 is 3, and 3 plus 6 is 9. So this is the new polynomial. This is 2t square plus 3t plus 9. For this new polynomial p plus q, the value at 0 is 9. Since it is 2 times 0 and 3 times 0 and 9. If these three are added, you get 9. Similarly, the value of this new polynomial at t is equal to 1, 2, 1 square, 2, plus 3 into 1 square, 3 into 1, that is 3, plus 9. So that is 2 plus 3 plus 9, 14. So this is the value of 9 plus value of p plus q. Here you can observe that if you add these two, 3 plus 6 is equal to 9 and 10 plus 4 is equal to 14. This is equivalent to this added polynomial. This is equivalent to this p plus q. This is p of 0 plus q of 0 is taken here, and this is p plus q of 0. Similarly, for scalar multiplication, I have taken a scalar 120. So I have multiplied with 120. This p 120 into 2, 240, 240 t square plus 5 into 120, 600 t plus 360. This is c of pt. The value of Cp at 0 is 0, 0 plus 360, 360. And the value of Cp at 1 is 240 into 1 plus 600 into 1 plus 360. That is, all these three are added, comes to 1200. Here you can observe that this is 120 times to this one. C times 120 into 3, 360, and 120 into 10 is 1200. So both are equal. So these values are numerically checked. Let us take one more example. This is one more example. I have taken different p and different q here. Both are added to here. This is p plus q. These are the values of p plus q at 0. This is the value of p plus q at 1. And these are the values after adding these two separately. P of 0 plus q of 0. And this is p of 1 plus q of 1 is here. This is the multiplication segment. So here I am doing that c times p of 0 is this one, both are same. Here it is multiplied with 120, 1 into 120 is 120, 4 into 120 is 480. So this is CP, this is equivalent to CP of 1. So we can see some more live examples also with this. Now I can take anything and take 11t square plus 6t plus 7 is as my first polynomial, and this is my q of t is 5t square minus 4t plus 8. This is the resultant polynomial. 11 plus 5 16, 6 plus minus 4 2, 7 plus 8 15. This is the p plus q of t, and we can observe that p of 0 is equal to 7. These two are zeros. P of 1 is equal to 1. This is the problem. These are the values to be taken here. So I have taken the values here. So p of 0 is equal to 7 and p of 1 is 24 after adding all these things. And this is q of 0 is 8, q of 1 is 5 plus minus 4 plus 8, and this is p plus q. This is p plus q of 0, both are tallied. So this is the value which from this new polynomial. This value is the addition of these two values. 7 plus 8 is 15. 24 plus 9 is 33. So these two are added here. Here this one is from this table. So you can prove any number of examples, but you can observe here that I can extend this. I can also write t power 3, t power 4 to any n. I can simply extend this. I can add these two. Simply I can add these two. I can also put some more values here. Instead of p of 1, I can put p of 2, p of 10. So any number of values I can take here. So you can construct simply, very simply, from Pn to Rn. You can construct a linear transformation from Pn to Rn for any n, and the results will be very instantaneous. So this is very useful in many areas. So you can take any Pn. Pn can be interpreted to many things, and that can be converted finally into some Rn. You can establish a relation between Pn and Rn very easily like this. So this problem can be extended to many real life problems also. And all the calculations will be done like this instantaneously. Here we can observe that this is the first property. T of u plus v is equal to T of u plus T of v. There is no discount or no loss while transmitting the data. C times this is C times T of Cu is equal to C times T. So for whatever scalar, there will be no loss of transmission and no discount. So these two properties of linear transformation can be used in many areas. Let us go back to our PPT. So we have done some of the experiments also there. So this is one more problem. Let us quickly go through it. define a linear transformation P2 to R2 by, here it is P of 0 and P of 0. In the earlier problem, it is P of 0 and P of 1. Here, both are P of 0. Find polynomials P1 and P2 in P2 such that span kernel of T and describe the range of T. So we know that P2 is the set of polynomials of degree at most 2, and P will be in this form as we have seen in the previous problem. P2 is a vector space and R2 is also a vector space. So this is the given linear transformation. So to find the kernel, we need null matrix, zero vector in R2. O is equal to 0, 0 is the zero vector. So P of T is in the kernel of T, then this P of 0 and P of 0 must be equal to 0, 0. P of 0 is nothing but A0. We have seen earlier. If you substitute P is equal to 0, you will get only A0. So A0 is equal to 0. So any polynomial in which A0 is 0 is in the kernel T. So if A0 is 0, the polynomial is in this form A1t, A2t square, where A1, A2 are scalars if it is in the kernel of T. So this can be written as kernel T is equal to A1t plus A2t square, where A1, A2 are scalars. So I have used two vectors, two polynomials here, T and T square. So this is equal to span of T and T square. So T and T square are the required vectors. Similarly, range of T will be like this, A0 and A0. Since we have it is P of 0, P0, P of 0 and P of 0, both are equal to A0 and A0, such that A0 is a scalar. So in the range, you can get matrices like this only. Both the entries must be equal. You can't produce 5, 4 with this linear transformation. You can produce 5, 5. You can produce 0.42, 0.42. So both the entries must be equal. Or finally, we can write it like this. Range of P is equal to set of C times 1, 1 such that C is a real number. So this is the range of P. So these are the problems on linear transformations. With this, I am concluding this class. Thank you for watching.